In this video, we're going to talk about the torque on a current carrying loop in a uniform magnetic field. So if you remember in the previous video, we went over this example here. So basically we calculated the force on a semicircular conductor. So again, the way we did this calculation is we calculated the force on the straight portion of the wire right here. So that was F1. We got a value that was 2I R times the magnitude of the magnetic field pointing in the K direction. And then when we calculate F2, this is the force acting on this this circular portion. So when we do that, we can calculate F2. So the first thing to notice is that we can write the ds vector as r d theta into negative sine theta I hat plus cosine of theta j hat. Then if you take the cross product of ds and b, so notice here that the b field is pointing in the j direction. So if you take the cross product of ds and b, you get negative IBR sine theta d theta k hat. And so if you plug that into this equation and you do this integral from 0 to pi, so again, the reason why we do this from 0 to pi is because if you look at this angle theta, it's going to go from 0 to 180 degrees. So if you calculate F2, you get negative 2IR B K hat. So the point here is that if you add F1 to F2, you get 0. So something that I want to take out of this is that the net magnetic force on the current carrying loop of wire is always 0, irrespective of the shape of the loop. So it doesn't matter if it is semicircular, circular, or rectangular, but once you have a loop of a conductor carrying a current placed in a magnetic field, then the sum of all the forces, the net magnetic force, is just going to be equal to 0. So now we're going to apply this concept here to look at the torque on a current carrying loop that is in the form of a rectangle. So again, notice in this example that you have a rectangular loop. The length is A, the width is B, and this carries a current that flows in the counterclockwise direction. And this loop is placed in a magnetic field, in a uniform magnetic field that is pointing in the I direction. So again, if you use the cross product, so what we can do is that we can calculate the force on side number 1, the force on side number 2, the force on side number 3, and the force on side number 4. Now, because side 1, if you look at side 1 here, is pointing in the opposite direction to the magnetic field. So here, so the current direction is negative I, and because the magnetic field direction is I, so if you do I cross I, you just get 0. Now, if you look at side 3, the current is pointing in the I direction. The magnetic field is also pointing in the I direction. So if you do I hat cross I hat, you also get 0. So side number 1 and side number 3 do not produce any contributions to the magnetic force. The only contributions to the magnetic force are going to come from side number 2 and side number 4. So notice that for side number 2, the current direction is pointing down. So that's in the negative J direction. The magnetic field is pointing in the I direction. So if you do negative J hat cross I hat, you get K hat. So it means that the force on side number 2 is pointing out of the paper. So it's in the K hat direction, it's pointing out of the paper. Now, if you calculate the force on side number 4, so for side number 4, the current is going up, which is in the J direction. The magnetic field is pointing to the right, which is in the I direction. So again, if you do I hat cross, if you do J hat, so the current is in the J direction. So if you do J hat cross I hat, you get negative K hat. So it tells me that the force on side number 4 is pointing into the paper. So you can even see that in this example right here. So the dot here means that the force is pointing out of the paper. The cross here means that the force is pointing into the paper. So now if I go and use my equation here, so again, because the magnetic field, so if you look at side number 2, the magnetic field is pointing at 90 degrees with respect to the direction of the current. So if I calculate the magnitude of F2 and F4, I just get IA times B. So this is the current times the length times the B field. No, so notice that there was supposed to be a sine of theta right here, but because the angle is 90 degrees, so sine of 90 degrees is just equals to 1. And so the magnitude of the force is just I times A times the strength of the magnetic field. Now I can calculate the torque. So if you remember, the torque is the force times the distance to the axis. So if this point right here, so the center of this rectangle is my axis. So it means that the distance from the center to this point here is B over 2, and the distance from here to here is B over 2. So I can calculate the torque, which is just the force times the distance to that axis. So when I calculate the torque, I get a value that is given by I times A times B. So notice that A here is just the area, which is the lowercase a times the B. So lowercase a times lowercase b gives me the area of this loop. So this is the maximum torque. And so because, so you have two forces that are acting in opposite directions here, it's going to cause this loop to rotate in the counterclockwise direction. So this is an example where you have the, so this will be the maximum torque that is acting on this loop of wire. All right. So now, so this is the example when you have the maximum torque. But now once the loop starts to rotate in the magnetic field, you're going to notice that the vector that is perpendicular to the surface of the loop, so it's called the normal vector, is going to have some angle with respect to the magnetic field. So on this picture right here, you can see that the normal vector is at 90 degrees with respect to the magnetic field. So this is when you have maximum torque. But here, the normal vector is not at 90 degrees with respect to the magnetic field. And so the torque is going to be reduced. So again, we can apply the same concept here. So because the force is not really at 90 degrees with respect to the distance to the axis, so we need to take this force and write it into x and y components. So for example, you can write this force as cosine of theta in this direction and sine of theta. So when you calculate the torque, you only use the sine because you want to use the component that is perpendicular, is at 90 degrees with respect to this axis. So when you calculate the torque, that comes from F2 and F4, and you do some simplifications, you end up getting this value right here. So this is I times A times B times the sine of this angle. All right. So now to put everything together, we can write the torque. So if you have a rectangular loop of wire in a uniform magnetic field, we can write the torque in this form. So the torque is just the torque vector is the current times the area vector cross the magnetic field vector. So so this equation here, we can also rewrite this equation as, so we can introduce a new quantity, which is just the current times the area vector, and this is called the mu value. So the mu is called the magnetic, this is called the magnetic moment vector. So if you just have a single loop, it's given by this, but if you have a coil with so many turns, then you can calculate the magnetic moment just by multiplying the I times the A by the number of turns. So generally, this is the final expression that we have right here. So in a magnetic field, once you place a magnetic moment in a magnetic field, it's going to generate a torque, and that torque is just given by the cross product of the magnetic moment and the B field. Now, when we calculate this magnetic moment right here, it says that if you look at this picture, it says that there is a way to get the direction. So if you just curl your fingers in the direction of the current around the loop, then your thumb is going to point in the direction of the magnetic moment vector. So again, this is a very easy way to calculate the torque. It's just a very simple equation. So just the cross product of the magnetic moment and the B field. All right. So now we're going to look at this example right here. So we're going to try to calculate the torque on a rectangular current loop in a uniform magnetic field. And so this is an example that is from the textbook. So this is problem number 33 from the textbook. So suppose that you have a rectangular coil, and this coil has 100 closely wrapped turns and has dimensions such that the area is 0.4 meters. So the length is equals to 0.4 meters and the width is equals to 0.3 meters. And then it says that if you look at, so it says that the coil is hinged along the y-axis and its plane makes an angle of 30 degrees. So this is the coil here. So the coil is actually sitting in the XZ plane. This is the XZ plane. It makes an angle 30 degrees with respect to that y-axis right there. Now for part A, it's going to ask us to calculate the torque exerted on the coil by a uniform magnetic field of magnitude 0.8 Teslas that is directed in the positive x-axis when the current is equals to 1.2 amps. So we want to calculate the torque, both the magnitude and direction. And then once I know the torque, I'm going to try to find out what is the direction of rotation of this coil. So again, if I go here, so the first thing that I want to do is to write down all the quantities that are given. So it tells me the number of turns. So the number of coils that I have here, the number of turns is just 100. I know what the length is equals to 0.4 meters. The width is 0.3 meters. The angle is 30 degrees. The magnetic field is 0.8 Teslas and the current is 1.2 amps. So the first thing is that I want to write my B vector. So my B vector is just pointing in the I direction. Then my magnetic moment vector is given by the number of turns, N, times the current, times the area vector. So if I want to calculate the area vector, then I can say that the area vector is just the length times the width times N hat. Now N hat is the vector that is at 90 degrees with respect to this surface, and I can calculate N hat by taking the cross product of J hat and the unit vector that is pointing in this direction right here. So the unit vector that is pointing in this direction here is just given by cosine of theta I plus sine of theta j. So if you do the cross product, you get your N hat, which is equals to negative cosine of theta k hat plus sine of theta I hat. So now that we know what my N hat is, I can calculate my area vector. And if I know my area vector, I can calculate my mu vector. So again, the torque is equals to mu cross B. And if I substitute everything here, I end up getting this value here. So I just get NIAB times the strength of the magnetic field times the cross product of N hat and I hat. So if you do the math, you end up with this equation right here. And then if you substitute all the quantities that are given, you end up with a value that is negative 9.98 Newton meters pointing in the J direction. So because this is pointing in the negative direction, it means that the rotation is going to be clockwise about the y-axis. So whenever you have a positive torque, so positive torque means counterclockwise rotation, negative torque means clockwise rotation. So in this example here, this loop, so this loop of wire is going to rotate in the clockwise direction.